Welcome to the demo session on the course FPGA-based signal processing system. So in today's demo, we will be implementing some FSM, finite-state machine on this ZedBoard. So let's start with the clock divider first. Since in the previous demo, we had implemented mod 4 counter with clock divider circuit, in which you can see that in the module section only I have introduced another module that having clock divider with the clock input and output, in which you can see that I am taking a divisible of 50 into 10 to the power 6 here, right? But we are moving it to the divisible minus 1, so it should be less than divisible minus 1, so it is less than 50 into 10 to the power 6 minus 2, and since it is less than not equal to, so it will run up to 4999997 only. So it is the approximate 1 Hertz, not the exact 1 Hertz, since we are losing 3 of the clock, like 3 into 10 to the power minus 9, 10 nanosecond, since the original clock is running on 100 megahertz and a clock period of 10 nanoseconds. So we will be losing some of the count, like divisible minus 1, so almost it will be 50 to 10 to the power minus 10 to the power 6 minus of 3 in the one go, and another again it will be 50 into 10 to the power 6 minus 3. So it will give the approximate 1 Hertz, not the exact 1 Hertz. For that, we have written another code that gives the exact frequency what we want in another fashion. We'll open a project since I have already created. We'll click on the open project. We'll move it into clock divider. We'll click on this XPR file. Okay. Now this will open. Now if we double click on this, it will be open on the text editor. Now I'll see that I am taking as a module clock divider, in which I am taking the input, board input as clock, CLK, and the output is divided clock. Okay. In this divided clock, you can see that divided clock will be our slow clock, and this is the board clock. Now I am defining an integer having count, initially having count 0. With every positive edge of the clock, it will count up to 1 into 10 to the power 9. See, in this one, what we are doing, we are moving around 10 seconds for one go and another 10 seconds per half cycle. So this is a clock divider circuit that we will be using in the next experiment, in which now if we want to show it on the LEDs, what we are going to do, we'll take a clock by 9 pin, that is 100 megahertz from the port, and the output I am implementing on the divided clock. I am just want to see the output from a LED. So if I open the constraint file for this, what it should have a clock. Clock will be taken from by 9 pin and it will run on the standard 1.8, again the LB-CMOS 1.8, and the divided clock I will be seeing on T22 pin on the FPGA board, that is the first LED on this board, and again it will run with 1.8 volt of logic. So since I have already generated the bit stream, I'll just open the hardware manager, just make sure the board is on, and we'll click on the open target, create. So it will be connected, like you can see that the board is connected and it is not programmed now. We'll click on the program device and we'll click on OK. It will start. So this blue LEDs will show that our board is programmed now. So see, for every 10 seconds the LED will glow, and again after 10 seconds it will be off. See, this is glowing. So for 10 seconds it is glowing. Again it's turned off. Again after 10 seconds it will glow. Okay, this is glowing. So our clock divider is working fine. We are doing it to show our output effectively on the board, but the board is already having 100 megahertz. So in the real time implementation, if you've done, the clock will be changing in 10 nanosecond every time. Okay. Now just opening some FSM code. That first I'll go with the implementation of sequence detector having 100 to detect the sequence 100. We'll click on OK. We'll close the previous project. Now it is opening. You can see that updated. Now I'll click on the sequence detector. See, this is a sequence detector having input as clock. Since it is milli, so it will be depending upon the current input and current state both. So I am taking the clock from this clock divider as it is for every 10 seconds it will be on, after 10 seconds it will be off. So the module name is sequence detector. I am taking as input clock, reset, sequence. Sequence we will be giving through the sliding switch, and output if is found then it will be the glowing LED. So our SREG and X next will be 2-bit, like SREG since it is having only 3 state, and again output as found it will be defined in the reds. To hold this clock divider, I am using Bayer as divided clock. Now I am defining the 3 parameter A, B and C over here. So A will be 0, 0, B will be 0, 1 and C will be 1, 0, right? Only 3 state B it is there, so it can be accommodated in 2-bit. Now before going to the next step, we are going to instantiate our clock divider, right? So for that clock divider, we have input and divided clock. The clock, this is the inside local module, it is the clock itself, and this is from the clock divider. Again, divided clock, it is in the local module, and this is from clock divider. So dot clock, in the bracket clock, dot divided clock, in the bracket divided clock. Now with the always block, either in the positive edge of reset or the positive edge of divided clock. See, this is divided clock now, not the clock. If we take the clock, it will be running on 100 megahertz, so that state will be changing with only 10 nanosecond. Every state it will change. For demonstration purpose, I had reduced the clock so that the state can be visible correctly. Okay, so with the positive edge of divided clock itself, suppose if the reset is 1, it will be A will be assigned to the current state as the divided clock will be 1. Again, in the case statement, again in the begin case statement, I am taking at if it is in the state A and the sequence is 0, it will stay in the A, else it will go to B. Suppose, so if it's in 0, it will be A, if it's 1, it will go into B. Again if it is in B state, again if we get the sequence 1, now it will stay in the B, otherwise it will go into C. Since again with the C state, if we get 1, it will stay in the B, otherwise it will go to A. Again default state we have to define, so the default state will be A, and it will be always, see that if it is 1, 0, 0, then found should be 1, otherwise it will be 0. So if we achieve the state 1, 0, 0, our LED, found LED will glow, otherwise it will be off. So this is the code. It is already explained in the lecture slide, you can refer to that. Now we'll click on the rel linter, it will check for any error. If I open the design, open the elaborated design again, see, it is expanding, initializing devices. So if we see the schematic over here, we click on the schematic, it will look like this. Inside that, if you expand that, you will get the circuitry of what we have implemented in the divided clock itself. Okay, now if I open the constraint file to this one, so if I click on next constraint file, sequence detector.xdc file, so we have a clock and divided clock, right? So the clock I am taking it by 9 pin, it's already in ZedBoard, and the divided clock will give the output at T22 pin, means the first LED will be used for the clock. Second, if we get the found, the second LED will glow, that is for T21. Again, N15 switch, that push button over the board, this one I am using as a reset, and F22, this sliding switch I will be using for giving the sequence. And since it is a melee, so the output will be depending upon the current sequence and the current state also. This is F22, again I'll give this sliding switch, we will be giving the sequence, and all this will be running on the LV CMOS 1.8, means low voltage CMOS 1.8 volt of logic clock, divided clock, found and reset, right? Again you can run the synthesis after that implementation, and you can generate the bit string. If you don't get any critical warning or error, it will be successfully generated. Since I had already generated, you can check the status here, right, bit string completed. So we'll click on the directly click on open hardware manager. No hardware target is open now. We'll click open target and auto connect over there. So now our board is connected from our PC. So you can state that it is board is already programmed with the previous, since we had implemented the clock divider previously. So the status will show programmed, right? We'll override with program devices. We'll give that bit file of this one, sequence detect.bit. We'll click on the program. Now say the board is programmed with this sequence detector of 100. You can check that status. This is the input we are giving with the sliding switch. This is for clock. The first LED, after 10 seconds it will glow. Again after 10 seconds it will be turned off. And this is if it found 100, then a second LED will glow. This is for reset one. You can use it for reset. Suppose in this one, now I'll change the input to 1 and check that it is giving the output or not. Again for off cycle also it should be 1, right? So once it will start glowing, we'll give it to 0. Now we'll give it to 0. Now just have a look. So when it will be 100, this LED will glow, the font should glow, right? So if it's on, it will be giving 1 again, the font will be 1. See, font you will get 1, right? So for the complete cycle, you have to give 1. Again, after it detecting 100, this should be 1. And this is for clock. Again since we are giving 0, right? So in the next clock, it will be 0, 0, 0. It should not blink, right? The output should not be 1. See, again with the clock, since it is 0, 0, 0, this will turn off. Right? You can verify it functionality by giving the another, again the sequence 1. It will wait for the 0, it will be again wait for the 0. Once it detect 100, the font will be 1, otherwise it will be off. So this you can verify by giving the switch, and this is the reset one. You can press this button to reset the state over there, right? So this is all about detecting the sequence 100 by giving the input from the sequence and the state it can take. Since it is a milli one, so it will be depending upon the current state and the current input also, right? Okay, this is all. So moving to the next sequence detector. Now in the next, we will be using some overlapping condition also, right? So sequence detector, this is again I'll going to open, we'll close the previous one. Okay, it is updating over there. If you double click on that, now I'm using the same clock over there, like I am instantiating our clock divider over there. This is the path. So it will be for 10 seconds it will be on, another 10 seconds it will be off, so that we can check the state very effectively. Otherwise, if it's running on the board clock, no, it will be changing the state in every 10 nanosecond. So it will be very difficult to check that. Either we are giving the input in 10 nanosecond and we are giving taking the output, it is glowing or not. Because changing of LED will be very fast, right? So to demonstrate that, I just reduce that clock. That is using divided clock over there. So again, for a state we need 2-bit, right? So the S rays having 2-bit, S rays and X next. This is the current state, this is the next state, and this is the found. Once we get the state 0, 1, 0, 1, so output will be 1, otherwise it will be off, right? So output will be the S rays, X next, and the divided clock. Now I am just plotting the current state also S rays over there, so that you can, in the LED you can say that what is the state over there at the current at the clock, what is the output over there. And one output also I am plotting the divided clock, so that it will be easy for me, it will be easy for us to changing the switch, to giving the 1010 sequence over there, right? So we have input as clock, reset, sequence. Output can be found if correct sequence is detected. The out will be S rays also, so that this 2 LED I am using to demonstrate the current stage, and the output will be the divided clock also. 1 LED will be used to check that our clock how it is moving. So it is found again by I am holding our clock, as in the by divided clock. It is used to hold our slower clock. This is the parameter, the 4 state I have to define, that A, B, C, D. This is the clock divider circuit. Again, clock will be synced with the internal module of this clock, and the divided clock with the divided. Now see, again with the process of the reset in the divided clock, it will stay. If the reset is 1, it will stay at 1 A, and it again otherwise it will be clock will be 1, and this will be executed. Now with the beginner statement, I am using the current state S rays. So if it A, if our sequence is 1, right? If our sequence is 1 and it is on the state A, it will be stay at stage A, otherwise it will move to stage B. See the first code, what is it itself? It is giving, if our state machine is in the A and the sequence is 1, it will stay at A, otherwise it will be moving to B. Similarly, if it is in the B state, if the sequence is 0, it will be staying at B, otherwise it will move to C. Similarly, D, C and D state also, the explanation you can check in the lecture slide also. Now with the S-rays in sequence, if S-rays is the like 1 0 1 0 1, if he get detected, then output it will give as 1, otherwise it will be 0. This is the output logic. This is the state how it is moving with the sequence. Suppose if A sequence is 1, it will stay at A, otherwise B. If it is in B, if the sequence is 0, it will be staying at B, otherwise it will go to C. If again in the C, if it's 0, it will go to D, otherwise it will stay at A. This is the output logic. So if it current detected 0 1 0 1, the output can be 1, otherwise it will be 0, right? If I open the constraint file over here, double click on that, you can check that this is S-rays and S0, right? So the first two LED I am using to give the current state, what it is, the first T21 is for S-rays 0 and the T22 it will be S-rays 1, right? T22 for S-rays 0, T21 for S-rays 1, right? The first two LED will be the current state, and by 9 is the clock itself. It is running on the LB-CMOS. All this will be running with the LB-CMOS 1.8 volt of logic, and divided clock you can check from U22 LED. U22, just have a look. This is the fourth LED. You can check the clock. This 2 is for current state, this 1 for found. If you get the current sequence, desired sequence, this will be glowing. Third LED will be glowing. Fourth will be for clock. First 2 will be for the current state, right? You can give, we will be giving the sequence from F22, means this sliding switch, right? And the reset can be given from this N50, means this push button. Now, since I had already implemented and generated the bit stream, I'll click on Open Hardware Manager directly. We'll click on Open Target Auto Connect. So this will be connected, right? Now we'll click on Program Devices. This is the sequence detector 010.bit. This is the configuration file for FPGA. We'll click on the program. Now the board is get programmed with this sequence detector 0101 overlapping case. Overlapping, what it means? Means if we are getting the sequence 0101, it will be on. Again, if we get 01, it will be on. It will be take 01 and 01 from the previous one, right? This is the case of overlapping. So see, it is in the state. This is giving the first 2 will be the state 10, and this is a clock. We have not found anything, so this will be off. Now see, with the clock I will be giving, since it is 0 now, I will be giving the sequence 1 with the glowing of this clock. Okay, I'll just give 1, so it will be 1. Again with the clock, this will change, though the state will change, right? So again it is 1 itself. So the glowing of LED I'll give 0. Okay, it is good. It is 0 now. The state you can observe that it will change. It will be now 0 1, right? State will change. Now if I give 1 again, see, if I give 1 again, the found should be 1, right? It's because 01 01 it will be. See, if I give 1, then output will be 01 01, found will be 1, and this state will be 1 1, right? Similarly, again again if I change it 0, it will be off now because the sequence get changed. To again with the clock, the state will change, right? I'll give 1. So by the help of this sequence, now you can detect that desired sequence that we are detecting it right now, 0101. You can detect any sequence over there. And it is overlapping, right? If we are going 0101, if it is glowing, again if we give 01, it will be glowing also, right? Since it is overlapping, this you can verify it from the giving the sequence, right? Now moving to the Moore machine, so we'll open Moore machine. Okay, the expired file, we'll click on that. We'll click on yes, we'll close the previous one. Now see, it will not have any sequence, right? It will depend upon the current state only. So again, I am using this clock divider to reduce our clock so that it can be easily visible on the board. And parameter, since it is on the 8th state, I am implementing this You can check that. This is the state. Okay, this is a Moore machine what we will be going to implement. So you can check that. See, this is the state. So if it state A with the clock, it will go to E. Again with the clock, it will go to C. Again with the clock, it will go to F, G, H, D, B. Again it will come to A. Similarly, for every clock, it will be moving their state, right? It will be moving to A, to E, to C, to F, to G, to H, to D, to B, to A. If I open that, you can check that we are taking the input as clock, and output I am taking the current state and the next state, both I am plotting on the LED. The first 3 LED I will be using it for current state, and the next 3 I will be using for next state, and one output, the corner LED, I will be using for checking the clock, right? So this is the parameter. Since it's a total 8 state is there, so we need 3 bit, right? So 0, 0, 0 for A, 0, 0, 1 for B, C, D, E, F. Similarly for H, it is 1, 1, 1. If the current state is A, means 0, 0, 0, then next it will go to it will go automatically to E. It means it will be 1, 0, 0, right? If it is in B, suppose if it in E now, see, the current state will be E, then next will be C. Next will be C. C will be 0, 1, 0, right? For every clock, it will be moving their state, what we have defined, right? So again, to hold our clock, we will be using byte over there. This is the from clock divider. I am using clock and divided clock. Clock will be synced with the clock in the current module and the divided clock also, right? So for the positive edge of divided clock, this is S raised less than equal to X next. With always block, I am taking with the both current state in this one. With the S raised and the passage of the clock, that's why I am giving the start. It will take both, right? So begin. It will be the S raise, right? The current state, if it is A, then it will move to E, again B, A, C, F, like this. I am just opening the constraint file for this. You will click on that. See, the constraint file for this is like T22 and T21. Like the first 2 LED, the first will be T22, right? It will be for S raise 2 and T21 for S raise 1, right? Similarly, the third one, U22, it is for S raised 0. You can check that 012. 012 means it will be from this one. This will be 0, this is for 1, this is for 2. Similarly, this is for 0, this is for 1, this is for 2. For the next, this corner I will be using for the clock, right? This 3 will be for the current, this will be using for next, and the corner for clock. And since we are not using any reset here, so this is the constraint file. Since I had already generated the bit stream, I'll just click on open target. It's already connected. We can directly program it over here. Now it get programmed. Now see, the current state is 0, 0, 0. Then it will be 0, 0, 1, 0, 0, right? Current will be 0, 0, 0. Then it should be 1, 0, 0. Again, the next, it will come 0, 0, 1, right? Again, for this state, 0, 0, 1, B, you can check that output will be A, right? Similarly, you can check the function like every clock, with every clock growing, the state will change, and similarly, the next state will also change. See, this is 0, 1, 0, the state will be 1, 0, 1, right? 0, 1, 0, the next state will be 1, 0, 1. Again, see, if this is 1, 0, 1, this is 0, 1, 1, right? Okay, again, the clock will blink, the state will change, this will also change. The current state will change, and the next state will also change according to the current state, right? See, you can verify the output by seeing this current clock, the S raise and the X next, the next one, and this is for your reference to checking the clock. So this is all about FSM. Mainly we have implemented sequence detector of 100 and 10101 overlapping, and this is for Moore machine in which the output is only depending upon the current state. So this is all about this demo, in which in this demo we have implemented some FSM, right? In the first, it will be the sequence detector detecting the sequence 100. Second will be the overlapping 0101. The third, we have implemented the Moore machine in which the state is changing with the changing the clock. All these 3 programs will be running with the clock divider circuit. That is, we are reducing the clock so that the output can be seen. This doesn't mean our board is running with the reduced clock, right? The board itself, for the real-time implementation, you can use it, the clock by 9 that will be running on 100 megahertz, and the changing state will be very fast, right? Thank you.